Well, thanks a lot. I just want to say again how much I think all of us appreciate the work that you've done and that the staff here has done. And this has been, I think, a very, very nice conference. Everything right up through the dinner last night. I mean, everything has just been very, very carefully and very nicely done. So I appreciate it. Okay, this is my last talk of the conference. I get to relax after. Let's see. So far the lectures have been all about Cm of Rn restricted to a finite set E. Okay, and today, well, all right. So that leaves open the question: what about infinite sets, and what about other function spaces? So we've heard from Kevin about infinite sets, and from Aryeh about other function spaces, and today's talk is going to be about other function spaces overlapping with Aryeh's talk. So today we're going to talk about extension and interpolation problems in Sobolev spaces. And this talk will be a light talk, no heavy lifting, no proofs of anything. Okay. All right. So to make this a very light talk, let me just recall the basic definitions and simplest properties of Sobolev spaces. Okay. So the space LMP of Rn consists of locally LP functions such that if you take their distribution derivatives of order exactly m, those distribution derivatives are LP functions. Okay? So notice we're taking derivatives of order exactly m. So for instance, a polynomial of degree m minus 1 belongs to this thing and has semi-norm 0. You're about to meet the semi-norm. There it is. Semi-norm is just the sum of the LP norms of all the distribution derivatives of order exactly m. Okay? So that's LPM. And polynomials of low degree have semi-norm 0. Okay, on the other hand, WMP of Rn consists of all functions in LP of Rn whose distribution derivatives up to order m, so it means f and all its derivatives up through order m belong to LP, and for that there's a norm, and the norm is what you see, let's say the sum of all the LP norms of the function and all its derivatives up to order m. Okay, now we're going to use the Sobolev theorem. Now there are different versions of the Sobolev theorem. This is actually a not very sharp form of the easier of the versions of the Sobolev theorem, but it's all we'll need. So if P is greater than the dimension n, then LMP of Rn is contained in Cm-1 loc. So locally, if you have m derivatives in LP, you have up to m-1 derivatives locally continuous, and WMP of Rn is contained in Cm-1 of Rn. So if the function and all its derivatives up to order P are up to order m are in LP, and P is greater than the dimension n, then your function has m-1 continuous and bounded derivatives. So that's just the Sobolev theorem. Again, one of the easier versions of the Sobolev theorem. Okay, now in fact the Sobolev theorem tells you other things. For instance, if P is not necessarily greater than the dimension n, but rather if P is greater than n over m, okay, then, well, you don't get m-1 continuous derivatives, but at least you get continuous functions as on the slide. Okay, now we're going to be thinking about interpolation problems. And so we're going to be, we will want to say that our function takes a given value at a given point. If our functions aren't even continuous, that doesn't mean anything. And so we should ask that P is greater than n over m, or else change the problem. Okay? And so there are interesting versions of this problem, which I'm not going to talk about, very, very basic versions when P is less even than n over m. But for us, we want continuous functions. All right, and I include a note in the interest of honesty. So there were plenty of lies last time. So far, there hasn't been a single lie. So strictly speaking, functions in LMP or WMP are, of course, LP functions, they're defined only up to sets of measure 0, but thanks to the Sobolev theorem, we can correct them on a set of measure 0. And so we can think of a function in a Sobolev space as being a continuous function. And I will always do that, okay? So our Sobolev functions for p greater than n over m are always considered to be at least continuous functions. And in fact, as you'll see, I'm really only going to talk about p greater than n, and then all our Sobolev functions have derivatives at an individual point up to order m-1. Okay, so all right, let's let X be the space we're working in. It's either LMP or WMP, and let's write that to denote the corresponding semi-norm or norm. All right. So now preparing to set up Whitney's questions. Suppose we have some arbitrary subset E in Rn. X of E is going to be the set of all restrictions to E of functions in X. And the obvious semi-norm or norm is just this. It's the inf of the norm or semi-norm in X of all functions F in the Sobolev space that agree with little f on E. So that's the trace space. Okay? And so again, for P greater than n over m, this makes sense thanks to the Sobolev theorem. And if P is less than or equal to n over m, unless, well, for let's say, if E is a point already, this doesn't make sense. Okay, so we will always assume here that P is greater than n, but our questions will make sense for P greater than n over m. Okay, so with those preparations, Whitney's problems can be stated for Sobolev spaces, and they will look very familiar. It's just that the space in question is a Sobolev space instead of CM. So the first question is to decide whether a given function on some horrible set E, let's say f takes E to R, and E is contained in Rn. Decide whether that belongs to X of E. That's the main question. But then, all right, given a function f in X of E, compute the order of magnitude of the norm. Well, maybe that's the main question. Does there exist a bounded linear map from X to E, from X of E to X that extends? So can you pick the extension to depend linearly on the function to be extended? And can you do it in a way that the norm is controlled? All right, we're going to be interested in algorithms. So given a finite set E contained in Rn and a function, we'd like to compute an extension capital F that agrees with a given function on E. A tolerance would be nice also, but let's walk before we run. So let's just try to get capital F to equal little f exactly on E, and with the norm or semi-norm of f having the smallest possible order of magnitude. How do you compute such a thing? What's a good algorithm? Okay. Now, again, I'm not going to go through the history, but neither do I actually want to slander anybody. So let me just say that great credit goes to Pavel Schwartzman, who understood Whitney's problems for the case of one derivative in LP for P greater than n, which changed the situation from, my God, it changed, I think, everybody's thinking, the thinking of everybody interested in the problem from, oh my God, how are we ever going to say anything, to, oh, look at that, it's possible to say something. Well, let's see what we can do. Okay. I want to mention Aryeh Israel, who understood the first case in which Whitney's extension operator doesn't work, and you have to work to pick correct jets, so that I think from the present point of view, it's fair to say it's the first non-trivial case. So the case L2P of the plane, two derivatives in LP of the plane for P greater than 2, and he introduced the idea of keystone cubes, which he mentioned a little in his talk, and which I'll mention some more at the end of this talk. So keystone cubes are the main difference. Once the dust has settled, keystone cubes are the main difference between what you have to do to handle Sobolev spaces and what you have to do to handle CM. And then I want to mention also Kevin Luley and Pavel Schwartzman independently understood LMP on the line. Okay. So, all right. Now the work I'm going to talk about is joint work with Aryeh and Kevin. And okay, so now I think maybe I've not actually slandered anybody. Okay, so again, constants denoted by the letter C, any version of the letter C, mean that they depend only on which function space you're working in. So if you're in that function space or that function space, you have parameters m, p, and n, and those are the only things that these constants are allowed to depend on. Okay, now the simplest version of our theorems is, all right, I think I'm trying to remember, I think there are going to be two theorems in the simplest version. So first of all, given any subset E in Rn, finite, infinite, non-measurable, whatever, given any subset, there is a linear map from x of E to x such that Tf is equal to f on E, and the norm of Tf in x is less than or equal to one of these constants C times the norm of f in the trace space x of E. And that's true for all functions. So that means there is always a bounded linear extension operator, and its norm can be taken to depend only on the parameters that entering into the function space. That's the first theorem. Okay. Then the next theorem has to do with computation of the norm. So now we're going to be talking only about finite sets E. Let's say, as usual, capital N is the number of points in E. Then there's a list of linear functionals on the trace space that we're going to use to calculate the norm. Okay. So how many linear functionals? Well, first of all, the number of these linear functionals is at most constant times the number of points of the set E. And we're going to use these guys to calculate the norm in the trace space. And so the statement of that is that for any function taking E to R, for a big finite set E, the way you can calculate its norm is that you simply evaluate all the linear functionals on this function little f, okay? And then you sum their pth powers and take the pth root, call that the triple norm of f. And then the claim is that the norm of, or semi-norm of little f in the space x of E is comparable to the triple norm. And therefore you can compute the order of magnitude of the norm of f in xe by using these linear functionals. Okay, now for finite sets, the linear map and the linear functionals have additional structure, and the additional structure will help us to compute everything efficiently. Okay, so let's go back to the theorem about the linear functionals. We have linear functionals on the space x of E. X of E is the space of functions on an n-point set. So each xi is a functional on an n-dimensional vector space, so it's given by n numbers. Okay? And so it looks as if there are ln numbers floating around here, and it looks as if the amount of work you'd have to do on a computer in order to calculate all of these x's applied to f is equal to L times n. But in fact, similarly for the linear operator T in the previous theorem, but in fact, thanks to the extra structure, we're going to be able to compute the norm in linear time. Let me not overpromise. You watch the statement of the theorem. But in any event, these linear functionals and linear maps have additional structure. I wanted to explain what the additional structure is and then say how that helps us to make efficient calculations. Okay? Okay. So the additional structure is what we call assisted bounded depth. So first I'm going to motivate the idea of assisted bounded depth. So suppose simply we're given n real numbers, x1 to xn, and our problem is to compute the variance of these numbers. So, all right, we all know how to compute the variance of n numbers, and here are two formulas that we learned as undergraduates. Okay. Now the first of these formulas, all right. So we look at the sum of the squares of the differences, and we divide by this normalizing constant. Well, in order to do that, just if you blindly code this up, you are summing over I and j from 1 to n, so that takes n squared operations. That's not so good. On the other hand, here's the other formula. I guess maybe this one is even the definition of the variance, where x bar is the mean. Now, if you have n numbers, look at this formula, and it takes O of n work to calculate the mean. And once you've found the mean, you come back to this formula, and there are only n terms, not n squared terms, so it takes only O of n work to do this. And so this formula is a whole lot better than that one. This one needs n squared operations. This one needs n operations. We like this one. We don't like that one. Okay? And the moral is that it pays to pre-compute. And therefore, we're going to pre-compute something, and that will help us to evaluate the stuff that we really want to know. Okay, so what are we going to pre-compute for Whitney's problems for Sobolev spaces? And we're going to pre-compute some assists. So, well, what does that mean? So let's suppose we have a linear functional omega from the space x of e to r. Now remember, E is a finite set. X of E is the set of all functions on E that, that can be extended. E is a finite set. Of course, every function on, I use this many times, every function on E can be extended. As a vector space, X of E is simply the set of all real valued functions on E, and it's only the norm that's interesting. Okay. All right. Well, now, since X of E is the set of all functions on E, guess what a functional omega looks like? It looks like that. You get to pick coefficients mu of x for x in E that don't depend on f, and omega of f is given by this formula. That's what linear functionals on a finite dimensional vector space look like. Okay? All right. So the depth of omega is simply the number of non-zero coefficients, and we denote it like that. So let's go back and look at the formula. This omega of f seems to be a great big sum, but let's say if there are only 11 non-zero coefficients mu, you can rewrite this in an obvious way as a sum of 11 terms, and it's then much easier to calculate omega of f than for a general functional. Okay, so that's the depth of a functional. Okay, now, all right, so given an f in x of e, the number of computer operations needed to calculate omega of f is like the depth of the functional. Okay, so we're going to be pre-computing a finite number of linear functionals. So this omega will consist of the linear functionals that we pre-compute. So a finite set omega of linear functionals on x of e, where e has n elements, will be called a set of assists if the sum of the depths of all the functionals in this collection is at most some constant times n. And I won't worry about which constant. Okay? So that's a set of assists. And the point about that is that if you have a set of assists and you are then given a function f on E, the work required to evaluate all of the functionals in the collection acting on omega, that total work is comparable to the work required merely to read the function f. Okay? So any algorithm that you perform on the function f will presumably require you to read the function f, and so this is essentially free. So a set of assists is a set of linear functionals that you can evaluate essentially free, working no harder than you would work simply to read the data. Okay, that's a set of assists. All right, so the assists are going to play the role of the mean x bar in the that x bar played in the computation of the variance of n given real numbers, namely for a given function f, omega of f for little omega in this capital omega, those are the objects that we're going to pre-compute that will help us to evaluate the things we really want. Okay? All right. So now that we know what assists are, we know what it is that we're pre-computing. Now let's define assisted bounded depth, and we'll see how the things that we pre-compute are going to help us. Okay. So again, E is our finite set with n elements. Omega is a set of assists, so it's a set of linear functionals on E. And now we have some other linear functional, like let's say one of our list. Remember in the previous theorem there was a list of linear functionals xc1 to xcl, so maybe this xc is one of those. In any event, this xc this linear functional, is said to have omega-assisted bounded depth if it can be written in the following way. Okay? So C of f is, well, here's the way it looked before. A linear functional could always be written as a sum of coefficients times function values, summed over the set E. But now we could also sum coefficients times functionals from the set of assists. So a given C can be represented, I mean, if there are some assists, it can be represented in more than one way. We could choose not to use any of the assists, and we could simply write the thing as before, or we could choose to make use of the assists and then simply include coefficient times assist, and then another coefficient times another assist, and so on. Okay? So here, that's the formula for all f. These coefficients are, of course, supposed to be independent of the function f, and this representation is sparse. So among these coefficients, lambda of x and omega of mu, there are at most a bounded number, there are at most c non-zero coefficients. So for example, suppose that we were computing the variance of a lot of numbers. Let's say our assist would be the mean of the numbers. That's a linear functional on x1 to xn. Okay? And then if you look at, let's say, x5 minus the mean, that has a long, complicated expression, namely x5 minus a small constant times x1 minus a small constant times x2, and so on. It has a long, complicated formula, but it has a very short, simple formula, namely x5 minus the pre-computed mean. That's a formula with only two terms. Okay? So that's what it means for C to be of assisted bounded depth. All right, I hope my light lecture isn't too light, but am I right? This is completely clear? Okay. All right. So the point is now, suppose we're given a set E, a set of assists omega, a linear functional C of assisted bounded depth, and a function f. Once we've pre-computed all of these omega f's, which, remember, we can do essentially free, then in order to calculate C of f, we can do it in O of 1 computer operations, because by assumption, our C has a very short description in terms of the stuff that we've pre-computed. Okay, so that's an assisted bounded depth linear functional. Now, I'm also interested in operators, in linear extension operators, not just linear functionals. So let's make the same definition, the definition in the same spirit for operators. So suppose, again, E is finite, omega is our set of assists. T is now an operator that takes functions on E to functions on Rn. So this is, of course, going in the theorem that I'm about to state. This is going to be our linear extension operator. Okay, the solution to the Whitney problem. Well, this T is said to have omega-assisted bounded depth if it can be expressed in the following way. Okay, so for each point x, T f of x is a functional acting on f, and we hope that that functional is a bounded depth. So that is, we can write it as a sum of coefficients times function values, plus a sum of other coefficients times assists acting on f, where these coefficients, of course, do not depend on f. So that's how, I mean, this tells us how TF depends on f. And for each fixed x, at most c of these coefficients are non-zero. So as before, there's a short formula. Okay? And so, as before, suppose we're given E, omega, T, and f. Then, well, once we've pre-computed the stuff that we can get essentially free, we can then calculate TF of x for any given query point x by using, at most, C computer operations. So it's real fast to compute TF at a point, but with one very important caveat. That's all very nice, provided that we know all these coefficients. So given a query point x, we had better be able to calculate these coefficients. Otherwise, we're in the strange position that there is a very, very simple formula for TF of x, only we don't happen to know what it is. Okay? All right, so those are the ideas of assisted bounded depth. And there's an interesting special case, namely suppose there are no assists. Okay, if there are no assists, then the notion of omega assisted bounded depth reduces to the earlier notion of bounded depth. In other words, we have short formulas without having to pre-compute anything. And so I've mentioned bounded depth in the previous talks. Okay, so now with those simple definitions, I can restate the previous theorems, but in a more precise form, making use of assisted bounded depth. Okay, so the theorem on extension is this. Suppose we have a finite set E in Rn, then there exists a set of assists and a linear map of omega assisted bounded depth, which does the job, which extends functions f so that Tf agrees with f on the set E where f was originally defined, and furthermore T is a bounded map from x of E to x. Okay, so our linear extension operator can be taken to have omega assisted bounded depth. Okay, and in terms of these linear functionals, in terms of the computation of the norm, the story is that given a finite set E with n elements, there is a set of assists omega. There's a list of linear functionals with the following properties. Okay, first of all, omega is a set of assists, so we can compute it essentially free. Each of these linear functionals has omega assisted bounded depth, so that means that each one of these can be computed incredibly fast once you know what omega is. And furthermore, the number of these is less than a constant times the number of elements of the set E. Okay? And those objects have the property that if you define the triple norm as before, the pth root of the sum of the pth powers of all these linear functionals, CL applied to P, then that triple norm is comparable to the trace norm of f, the norm or semi-norm of f in the space x of E for all functions f. Okay? So those are the theorems in the more precise form. So that means, let's see, this theorem on the computation of the norm means that maybe you do a whole lot of work, or maybe you don't even know how to find the coefficients of the assists and of the x's, but if an oracle told them to you, then given any function f on the set E, you could calculate the order of magnitude of its norm in linear time. But these theorems still don't tell you you can actually compute anything. Okay, before I get to the question of whether we can actually compute anything, let me ask a natural question. Do we need the idea of assisted bounded depth? Could we get rid of the assists and simply say that our objects have bounded depth? Okay, so is there an extension operator of bounded depth? Is there a formula for the norm in which the linear functionals have bounded depth? Well, for the theorem on the bounded linear extension operators, the answer is no. Okay, there is not in general an extension operator of bounded depth. We have a counterexample. What exactly does a counterexample mean? Of course, for any particular finite set, it has a bounded number of elements, and therefore any operator has bounded depth. But what I mean is this. The bound on the depth is supposed to depend only on which function space we're working in. And for a fixed function space, I can give you a sequence of finite sets such that the finite sets so that there does not exist a sequence of linear extension operators whose norms as operators are bounded independently of where you are in the sequence, and are of bounded depth, where the bound for the depth is also independent of where you are in the sequence. So that's the precise logical meaning of the statement of the word no in this case. Okay, so we can't make do with bounded depth. We need assisted bounded depth. For the theorem on the computation of the norm, the situation is more interesting, and the answer is maybe. Okay, so we don't know, and there's an interesting possible connection to sparsification. Sparsification is an amazing thing. I wish I knew more about it. if I had to give 6 or 7 lectures instead of 5, I would be saying more about sparsification. This is due to these people, Batson, Spielman, and Srivastava, and without getting into any details, let me just say that this magic word sparsification includes the fact that there is a formula for the variance of n numbers in O of n operations without pre-computing anything. Okay, so this is an amazing idea, and it seems that it can be applied. And so I want to thank Boaz, and I want to thank Asaf Naor for explaining that this subject exists and pointing out its possible relevance to this subject. And I want to mention also, so now the slide I think is too ambiguous. I'll explain what's going on. I want to see also the work of Pavel Schwartzman on sparsification for LMP when you're taking 1 derivative or 2 derivatives. So the situation is that Pavel showed that in fact sparsification does apply to these cases, and one can therefore give formulas where the functionals are of bounded depth. And so he and I have just recently come from very long nitpicking sessions in which I make him prove everything that I don't find instantly clear. And we are 99% through it. And I mean, the probability that at this point, the probability that I, well, he's a grown-up. He doesn't need me to say that it's correct. But the probability that I will be in a position to swear that it's correct is very high. Okay. All right. So it would be very interesting to incorporate those additional ideas into the previous stuff and try to get rid of the assists in the theorem on the computation of the norm. However, for purposes of efficient computation, we may not want to. That's another story, so I'll get to that. All right, now, so far, everything I've discussed has been written down and very, very carefully checked, with the sole exception that the remaining 1% in Pavel's thing, he is carefully checked. I can't swear, but okay. But, all right. Now I would like to take a chance and show you stuff that I'm quite confident is right, but has not been completely written up and therefore has not been nitpicked to nearly the same standard. And so there is the chance that it is just wrong. With that in mind, let's go on. Okay, so the next theorem says that we can compute everything. I guess the next 2 theorems. So in the next 2 theorems, suppose that, well, all right, so using at most Cn log n operations and at most Cn storage, we can compute the set of assists, and we can compute the list of functionals, C1 to CL, satisfying the conditions of Theorem 4. What that means is that if you give me a set with n elements, but not yet a function, f, on that set, just you give me the set, I will go back and do n log n work in space n, and I will come up with everything I need to pre-compute. And then if you then give me any function f, I can do linear work, work comparable to what it takes to read the function f, and I can return to you the order of magnitude of its norm. So that means things can be efficiently computed. Regarding the linear extension operator, okay, I'm not going to restate the hypotheses, but the claim is that there exists a set of assists and a linear extension operator which can be efficiently computed. So what does that mean? Okay, so we can efficiently compute all this stuff. What does it mean to compute it efficiently? Well, we can compute the assists using at most Cn log n operations and at most Cn storage. Okay. Moreover, after one-time work at most Cn log n, using storage at most Cn, we can answer queries. What's a query? A query is a point x in Rn, and the response to the query is a formula like this, explaining what Tf of x is. Now, of course, this formula looks very long. We're summing over all the points of E, and we're summing over all the assists. But the whole point of this is that a whole lot of these coefficients are 0, and any coefficients that are 0, we just drop from, whenever the coefficients are 0, we do not make the stupid mistake of including that term in the equation. So what the query algorithm will return in response to a query X is a short formula for TF of X. So, all right, and how much work does it take to answer a query? The work it takes to answer a query is big O of log n. So given a point, we can efficiently decide what is the formula for TF at that point in terms of F. And as an immediate corollary, we can extend functions because we know how to compute the extension operator efficiently, so we can just apply it to our function. And so suppose we're given a set E, as usual, capital N points, and we're given a function, and we would like to extend it with essentially the optimal Sobolev norm. Well, we can perform one-time work, big O of n log n, in storage big O of n, and then answer queries. And in this case, a query consists of a point x, and the response to a query is, let's say, f of x, or if you're more demanding, f of x and its derivatives of order up to m minus 1, because they exist pointwise. Here, capital F, which hasn't been previously mentioned, is our extension. So capital F is some function that agrees with little f on E, and its norm is less than some constant times the minimum possible. Again, this C depends only on m and n. And the work to answer a query is at most C log n. So that puts us in very good shape. That means that, well, maybe this is slightly overstated, but the above results bring our understanding of Whitney's problems for Sobolev spaces close to what was achieved earlier for CM. So, so far this doesn't include tolerances, and it doesn't remove outliers. I'm quite sure tolerances can be included in the machine. In fact, for one derivative in LP, Pavel has actually solved the problem. Let's see. Removing outliers might be trickier, a lot trickier. I'm not sure. Okay. Let me just point out that all of that happens when P is greater than n. When P is greater, if our derivatives belong to LP, where P is greater than the dimension, and we use the Sobolev theorem. Okay. Well, what happens if P is less than n? So let's say P is more than n over m, but less than n. And the answer, the answer is I don't know, so I hope you enjoyed the talks. Okay. Well, so as the slide said in my last talk, we got through it.